Today we're going to do some live coding, and we're going to do something which sounds impossible but is actually quite natural and practical, and that's programming with infinite data structures. And we're going to be using Haskell for this, but it doesn't matter if you don't know anything about Haskell because I'm going to explain everything in a simple way as we go along. The first thing we're going to do is we're going to start up the Haskell system which we're going to be using, which is called GHCI. And if you'd like to try this stuff out for yourself, this is freely available online, just search for the obvious thing. Before we start thinking about infinite data structures, we're going to do a little bit of computation with a simple finite data structure, which is a finite list. So here's a finite list in Haskell. It's just a list of numbers between 1 and 20, and it's written 1.20. And if we ask the Haskell system to evaluate that, it will just expand it out to give the numbers between 1 and 20. And then we can think, well, what can we actually do with a finite list? So for example, we could sum the list up and we get the expected answer, 210. We could say, well, maybe we want to square all the numbers between 1 and 20. So we can map the squaring function over the list from 1 to 20, and we get the first 20 squares. What else could we do? Well, maybe we want to filter out the even numbers from the list between 1 and 20, and we can do that. We just write filter even from 1 to 20. Or if we wanted to be a little bit more fancy, we could combine everything we've done up to this point, and we could say, what is the sum of the squares of all the even numbers between 1 and 20? And hopefully 1540 is the correct answer. So here's a little example of a finite list, 1 up to 20, and then we've seen 4 small examples of simple kinds of computation which we could do on that finite list. But the video today is about infinite data structures, and in particular we're going to be talking about infinite lists. So how do we do infinite lists in a language like Haskell? Well, it's very simple. Rather than writing something like 1.20, we just say 1 dot dot, and when I press return, this will be the infinite list of all the natural numbers beginning with 1. And this is going to go on forever, but I can interrupt it, and you can see we've already got up to about 196,000 here. Okay, so it runs quite quickly. So this is an infinite list. So what can we actually do with an infinite list? So let's try some of the things which we tried before, first of all. So maybe we can sum it. So let's try summing the infinite list of all the numbers beginning with 1. And I press that, and of course this doesn't actually work because there's an infinite number of values in this list, and we try and sum them all, it's never going to finish. So I need to interrupt this one here. Let's try something else. Maybe I can try filtering the even numbers from an infinite list, and hopefully this will work. And yes, it does. What we get this time is we get the infinite list of all the even numbers. Okay, so you can see there's no odd numbers in the list here. What we're actually doing is we're taking an infinite data structure as an input, we're taking an infinite list, and we're processing it, and we're giving an infinite data structure as an output. We're taking an infinite list in and giving an infinite list out, which is quite an interesting idea. So let's try another example. Let's try filtering all the numbers less than 100 from the infinite list, beginning with 1. And this kind of works, but not quite. There's a little problem at the end. So we get all the numbers from 1 up to 99, which is exactly what we expect. But now it's just sitting here. And that's because it's basically trying to find another number which is less than 100. And it will never succeed with that, but it doesn't know it's not going to find one. So it will go on forever. Okay, so I have to break out of this one. And this, again, illustrates the idea that when you're programming with infinite data structures, you need to be careful. We tried to sum an infinite data structure, and it didn't work. It just went immediately into an infinite loop. We're trying to filter here from an infinite data structure, and it gave us the expected results, but in the end, it just hung. So you need to be careful with this kind of thing. Let's try one more example. Let's try taking 20 elements from the infinite list beginning with 1. And this, of course, works. We just get exactly what we expect. We get the numbers between 1 and 20. We're taking an infinite data structure as an input. We're taking the infinite list of all the values from 1 onwards, and we're getting a finite data structure as the output. We're getting a finite list of all the numbers between 1 and 20. How does this kind of behavior actually work? And it's to do with the evaluation order which you have in your programming language. Most languages are what's called strict or eager. And that means when you have a parameter like this infinite list, you completely evaluate that parameter before you try and do anything with it. So if you're in an eager or strict language and you try and run take 20 of an infinite list, it's never going to get anywhere because it will just attempt to evaluate the infinite list, and that will never stop, and you'll never actually get any result. But languages like Haskell are lazy. When you have a parameter in Haskell, you only evaluate it on demand. So the demand here is that we want to take 20 elements from the infinite list. So the two parts here, take 20, and the infinite list, they kind of collaborate together and say, well, we only actually need to generate 20 elements to proceed, so we don't actually generate the entire infinite list. So in Haskell, when we write 1 up to infinity, it's not really an infinite list, it's a potentially infinite list, which gets evaluated as much as required by the context in which we use it. Here's some small little examples. Let's maybe try something a bit more interesting now. Let's try and write a program which generates all the prime numbers, the infinite list of all prime numbers. So let's remind ourselves what a prime number is. So a number is prime if it's only factors, so that's the numbers that divide into it exactly, are 1 and itself. So for example, 7 is prime because it's got 2 factors, 1 and 7, but 15 is not prime because it's got 4 factors. So let's write a program to do this. So first of all, we're going to write a small function called factors, which is going to return all the numbers which divide exactly into a number. So if I give it a number like n, I'm going to return all the values x, such that x comes from the list 1 up to n, and if I take the remainder, when I divide n by x, then that had better be 0. So this is just running over all the numbers between 1 and the given number, and I could be clever here and write square root of n, but let's just keep it simple. You run over all the numbers between 1 and the given number, and you just check, is the remainder, when I divide 1 by the other, 0? So for example, if I say, what's the factors of 7? I just get 2 factors, 1 and 7, so that's a prime number. And if I say, what's the factors of 15? I get 4 factors, 1, 3, 5, and 15, so that's not a prime number. And this tells us basically how we can define a very simple program to check if a number is prime. I can say a number n is prime if and only if I look at its factors, if I get back exactly the list 1 and n. So that's my definition of what it means to be a prime number. Now I can check that this actually works. I can say, is 7 a prime number? And it says true, because it's exactly 2 factors. And I can say, is 15 a prime number? And I get false, because it's got more than 2 factors. Now we've got all we need to actually generate the infinite list of all prime numbers. And you can do this simply using the filter function. If we just now filter all the prime numbers from the infinite list beginning with 1, then as soon as I hit return, this thing will start generating the infinite list of all prime numbers. Okay, and you can see here, it's already gone quite far. We've got up to about 16,000, and you can check that all of these numbers are actually prime. But actually, this is quite a modern laptop. We'd expect this program to run much faster than this. So what we'd like to do now is see how we can take this simple means of producing the infinite list of all the prime numbers and actually make it go a lot faster by using a 2,000-year-old algorithm.
Did they have algorithms 2,000 years ago?
Yes, they did. The ancient Greeks discovered many things, including many interesting algorithms. So here is a 2,000-year-old algorithm, which is called the sieve of Eratosthenes, after a Greek mathematician. And this is a very, very simple algorithm for generating the infinite list of all the prime numbers. So let's see how it actually works. The first step is we write down the infinite list, 2, 3, 4, all the way up to infinity. The second step is we mark the first value, p, so that's going to be 2, as being a prime number. The third step is we remove all the multiples of p, so initially that will be 2 from the list. And the fourth step is that we go back to the second step. So it's a very simple 4-step process for generating all the prime numbers. And an interesting observation here is that infinity occurs all over the place in this algorithm. We're writing down an infinite list at the beginning. We're removing an infinite number of elements from an infinite list in step 3, and then we're having an infinite loop in step 4, because we're looping around here forever. So let's see how this 2,000-year-old algorithm actually works in practice with a little example. So the first step in the algorithm was we write down all the numbers from 2 up to infinity. So let's stop at 12, but of course, in principle, we go on forever here. Then the next step is we mark the first value in the list as being a prime number. So we'll say 2 is our first prime number. Then we need to remove all the multiples of 2 from the list. And let's do this by putting a small barrier under all the multiples of 2. So that's the even numbers. Oops, I forgot 11. And we'll think of these barriers as kind of stopping these numbers falling down the page. So we imagine the numbers trying to fall down the page now. So the 3 will fall down, the 5 will fall down, and in general all the odd numbers will fall down because the even numbers are stopped by the little barrier. And you can think of this as being a sieve. This is why it's called the sieve of Eratosthenes, because we're blocking some numbers from coming down the page. And now we go back to the start again. So 3 is a prime number. And then we put a small barrier under all the multiples of 3. So 6 is already gone, 9 and 12. And then the numbers that are not stopped by the barrier are sieved out. They come down the page. So 5 comes down, 7 comes down, 11 comes down. We continue. 5 is a prime number. We remove all the multiples of 5. The numbers come down the page, and so on. So you can see the basic idea here. We're generating, in a very simple way, all the prime numbers. We're getting 2, 3, 5, 7, and eventually we'll get 11, and so on. So that's the algorithm. What we're going to do now is think, how can we actually implement this in our programming language? And we'll see that we actually only need a 2-line program to implement this. It's a very direct translation of the 2,000-year-old algorithm into an actual working program. So let me start up an editor, and we're going to write a program now. So we're going to generate the infinite list of all the prime numbers, and I'm going to define that by sieving the infinite list starting from 2. So the first step of the algorithm was we write down all the numbers from 2 onwards. So that's what we've got here, and then we're going to pass it into a function called sieve, which we haven't written yet, which is going to do all the other steps for us. So what does sieve do? Well, sieve is going to take the list apart. So p will be the first thing in the list, so that's initially going to be 2. And p's will be everything else, so that's 3, 4, 5, etc., all the way up to infinity. And then what we're going to do on the right-hand side is we'll keep the first value, so that's like marking the first number as being prime. And then we're going to recursively sieve something. So what we're going to do is we're going to sieve out all the numbers which are not multiples of p. What this part in the brackets here does is it takes the infinite list of all the remaining numbers, so 3 all the way up to infinity, and it's going to remove all the multiples of 2. So it's just running over the list, and it's removing all the numbers which are multiples of 2. So this will remove the 4, the 6, the 8, and so on. And then we just call ourselves recursively again. And this is the entire program. So actually the program is shorter than the English description we had of the algorithm. It's useful to actually think, how does each step actually get represented here? Well, the first step was we write down the numbers from 2 up to infinity, which is here. The second step is we mark the first value as being prime, so that's the value p here. The third step is we remove all the multiples of p, so all the multiples of 2 initially from the list, and that's the part here. And then the final step is we run the algorithm again from step 2, and that's calling the sieve function. So we've got our program here. So let's see it actually working. So let me start up the Haskell system again. Good, we've got no errors, which is good. So let's run the prime number program. And here we get all the prime numbers again. So it gives exactly the same results as the simpler algorithm, which we wrote before, but it does so a lot more quickly. And if you do some simple experiments, for numbers up to this kind of size, it runs about 10 times faster than the simple algorithm, which we had previously. So what could we do with this? Well, we could do a whole bunch of things. So for example, if I wanted 100 prime numbers, I don't now need to write a program which generates 100 prime numbers. I just take the infinite list of all the prime numbers, and I take 100. So I've kind of separated my control part, which is taking 100 numbers, from my data part, which is having an infinite list of primes. And this idea of separating control and data using infinite data structures is a very powerful way of thinking about programming. And I can do other things as well. So for example, if I wanted to say, give me all the prime numbers less than 100, I don't need to write a separate program for that now. I just take my infinite list of all the prime numbers, and I say take while less than 100, and I get that. And in many languages, if you wanted to write these 2 separate programs, you'd need to write some separate programs, basically. But if you can manipulate infinite data structures, you just have your infinite list of primes, and then you can do whatever you want with them afterwards. You can select what parts you like. Just to conclude, let me do one final little example to do with what's called twin primes. So twin primes are primes which differ by 2. So 3 and 5 are twins because they differ by 2. 5 and 7 are twins because they differ by 2. 7 and 11 are not twins because they differ by 4. So how do we write a program using what we've already done that generates all the twin primes? So first of all, let me say what it means to be a twin. So I'll say a pair xy is a twin if y is x plus 2. So for example, if I say is 3 and 5 a twin, it will say true. And if I say is 7 and 11 a twin, then I get no. So how do I use this to write a program that generates all the twin primes? Well, what I'm going to do is I'm going to generate the infinite list of all the twins, and I'm going to simply filter twin from zip of primes and tail primes. So there's a couple of bits we haven't seen before here. What does tail do? So tail takes a list, which could be infinite, and removes the first thing. So if we write tail of primes, what we're going to do is take the infinite list of all prime numbers and throw the 2 away. So we'll get 3, 5, 7, 11, etc. What zip does is it takes two lists, and they can be finite or infinite. So suppose I've got two lists of 5 numbers. What zip does is it pairs up the corresponding elements in the two lists. So it pairs up the first thing, the second, third, fourth, and fifth. So what it's going to do here with the infinite lists is we're going to zip the infinite list of all the prime numbers with the infinite list of all the prime numbers apart from the first one. So what we're going to get coming out of this zip is an infinite list of pairs of each prime number and the next prime number. So we'll get 2 and 3, 3 and 5, and so on and so on. And then all we're going to do is take that infinite list of all of those pairs and filter the twins out of it. And this is enough to generate all the twin primes. So I can test this out. Here's all the infinite list of twin primes. And this is a one-line program to do this, based on a two-line program which we had to generate the infinite list of all the prime numbers. Going back to where I started, programming with infinite data structures sounds impossible, but as we've seen today, and I hope to have convinced you, it's actually quite simple and natural and practical.
Okay, that's all because Haskell's lazy.
Yeah, it's because of laziness. So you can do this in other programming languages, but essentially you need to fake lazy evaluation in some way. And languages are providing a bit more support these days for doing that. There's kind of